In this class, we're going to look at some further connections between vectors, systems, matrices, and so on in the visual context of lines and planes and objects, straight objects of this sort that I assume you're already familiar with. To begin with, I'm going to remind you of some things that you should know very well, and that is the basic forms of the equation of a line. If you look at a line in two-dimensional space or in the xy plane, you know that there are several ways of describing it. One of the most common ones is what is called the slope-intercept form, and that's the one where we write y as mx plus b, where m of course is the slope and b is the y-intercept. Another one is the point slope form, in which we use, instead of the slope and the intercept, the slope and a generic point whose coordinates in general are denoted by x0 and y0 to begin to denote the fact that this is some kind of a starting point. Now notice that both of these forms apply and can be used as long as the line is not vertical. So for a vertical line we need a different kind of equation of the kind x equal some number. However, there is one form of the equation of a line which includes also horizontal lines, and for that reason it's called the general form. And the general form looks like ax plus by equals c. Notice that you can sort of navigate between these three different forms if you have the correct kind of information, as long as, again, of course, the line is not vertical. Otherwise, the last one is the only one that we can use. Now, what happens is that in linear algebra, we can use all the concepts that we've seen so far, both about vectors and about lines, to see and use different kinds of forms for the equation of a line, and that's what we're going to be starting to look at right now. The first type of equation that we're going to see is something called the normal equation. Normal, not in the sense of usual, the run-of-the-mill, everyday kind of thing, but normal as in perpendicular, because this equation uses a direction which is perpendicular to that of the given line. Let's see how this works. So let's say that we have a line. And let's say this is a line. I'm drawing it in this particular position, but it could be anywhere. What I'm going to say does not depend on that. Let's assume that we have a point on it, and let's call it, just like before, x0, y0. Okay? Now, if I pick any other point on the line, I can do the following thing. I can do the following construction. First of all, I can construct the vector that joins x0, y0 to xy. And of course, that's going to be given by x minus x0 as first component and y minus y0 as the second component. Now, notice that if I consider a vector which is perpendicular to this line, of course there is only one direction which is perpendicular to it, therefore every vector which is perpendicular to the line will be proportional to this particular vector. Then the fact that this vector is perpendicular to the old one, the one you see in front of you, tells us that the dot product of these two is going to be equal to 0. All right. Let's do some algebra on this equation. Remember, one of the properties that we have noticed about, that we have learned about dot product, is that it is distributive, which means that I can split the left hand side, and I can rewrite this equation as xy dot n1 and 2, and then that leaves me with minus x0 minus y0 dot n1 and 2, which I move to the other side, thus obtaining x0 y0 dot n1 and 2. Alright, so this may look like a pretty esoteric form, but it turns out to be quite useful in terms of the information it contains. Okay? This is what we call, in fact, the normal equation of a line, because it uses, if you notice, the first vector that we see in this form, this vector here, is actually the generic vector that identifies a point on the line. Notice I'm identifying a point with its vector. Okay, and this is something, again, that I've mentioned in the past and that we'll be doing on a regular basis. However, you want to make sure to remember that it is an identification and that really vectors and points are not exactly the same thing. Anyway, xy is the generic point on the line, and 1 and 2 is the vector perpendicular to the line. x0, y0 is one point on the line, and then of course we have the n1 and 2, which is repeated. So this is called the normal equation because it's heavily emphasized on the concept of the normal vector. Now we can write this equation in an even easier and simpler and shorter way in this way. which is a form which actually emphasizes again the components, the meaning of all the vectors that we have in the formula. So x is the generic vector that corresponds to the points on the line. N is any vector perpendicular to the line. P is any specific point on the line, or is a vector corresponding to a specific point on the line. And again, N is repeated twice. Now, if we expand the dot product that we see here, we end up with the following expression. If you expand on the left hand side, you end up with n1x plus n2y, and on the right hand side, well, when all is said and done, all those four numbers multiplied as scalars, they just give us a single number that we're going to call c. And this, of course, is equivalent to the general equation ax plus by equals c. Only again, it's written in a different way that emphasizes the role of the different vectors involved.